We know that neurons, the main property of neurons is that they're excitable. They can start to fire, and they can fire an action potential all the way down the length of an axon. So if I'm thinking, how do I get from the point that I consciously think about my toe wiggling, how do I get that to fire? How does the central nervous system communicate all the way down to the effector target? And we know the effector target. Well, first let's take a look at the structure of the neuron that I've drawn out for you, just to save a little bit of time. We have our dendrites to the left, we have the cell body, we have the axon terminal. That you should already be well aware of. And our effector target is going to be either a muscle, another neuron, or a gland. We don't talk so much, we will talk a little bit about muscles when we look at our peripheral nervous system. We're talking about neurons now because we're going to be talking about we're going to be talking about the inner neurons, the neurons in the brain receiving information. So if you can think of this as a brain cell, this is somewhere up in the cerebrum, we're going to be receiving information, sensory information that's leading to the dendrites of that inner neuron. And we're going to see that it's going to now target back out to another neuron or to a muscle. So how do we complete that loop? How do we start from receiving information down to the inner neurons, which is going to be integrating that sensory information, and leading out to the effector pathway? So now with that in mind, we have to start off talking about how the neuron is at rest. So what we're going to be doing is I'm going to start to paint that picture, but as I go through, I'll ask you guys questions. And what you guys can do amongst your group is nominate somebody. Feel free to point at somebody now. Nominate somebody to be able to answer that question. Because now that you've met with your group, you've talked through this piece, you should be able to answer these. So we're going to start off looking at the characteristics. I've already drawn out the structure. And now we have to take a look at the ions. I'm going to draw the ions in a different color here. And what we need you guys to do right now is to take a look at the ion concentrations. So I'm going to have you guys first tell me, and I'm going to start off with our group here in the very front, right? Where the concentrations of ions are. First tell me the three ions that we're going to be talking about in the neuron.
Sodium, potassium, and chloride.
Sodium, potassium,
Calcium.
and calcium, right?
Yes, calcium.
Now that we know that, these are our three ions. Now I want you guys to tell me where the highest concentration of sodium. Is it extracellular or intracellular?
Extracellular.
Extracellular? Okay, so we have high concentration of sodium on the outside. Appreciate the enthusiasm. Next group, where do we see the highest concentration of potassium? That's a group in the back. And the inside. And then this group, where's the highest concentration of our third ion, which was calcium? Where's the highest concentration of that? Where would we find that? Well, inside or outside? Inside? Outside. You have a slide that points out where those concentrations are. Okay. All right, so now that we've established those, we've looked at the ions, and now we know the direction of ion movement, right? The direction of ion movement is always from a high concentration down to a low concentration. Again, if you were guys a bunch of potassium ions, and I shove you all inside a cell, and there's leaky channels that are open all the time, you know you're going to want to go from a high concentration down to a low concentration. So the types of channels. The types of channels that we're going to be talking about, we're going to talk about leaky channels. And these leaky channels are non-gated, they're always open. Right? And we're going to be specifically talking about our leaky potassium channels. And then we have our gated channels. Gated channels can be divvied up into And let's start with our group in the middle. What types of gated channels do we have? Voltage and ligand. And if you guys are wondering about like writing all this down, don't worry, I'll send this out to you guys. This will be your review. Okay? So gated channels, we have a voltage gated and ligand gated. Now, given the characteristics of that, where would we typically see our ligand gated channels? That's our group in the back. Ligand gated channels, where would we typically see those? Well, first maybe describe what exactly is a ligand. Anybody? What's a ligand? What's a ligand that we're talking about in a neuron?
This activation.
It's okay, I'll give you a clue. A ligand is something that signals. It has to attach to something to allow it to open.
Substrate.
Okay, substrate. What's the substrate that we'll be talking about? I'll give you another clue. It's taking place in the synaptic cleft. Neurotransmitter. Okay? So the ligand in this case is going to be the neurotransmitter, right? Meaning that the neurotransmitter needs to bind to a ligand-gated channel on here. And once that neurotransmitter binds on, here I'll just draw it out for you. Neurotransmitter binds onto a channel, it's going to open it up. And depending on what neurotransmitter binds in, remember we talked about a couple of our neurotransmitters. Okay. Some of the neurotransmitters I talked about are excitatory. And best example for an excitatory neurotransmitter would be glutamate. So if glutamate binds in to one of these channels, it's excitatory. Would be excitatory. And then something like GABA would be inhibitory. We'll talk about that in just a bit. All right, so now that we've established that, so we've talked about types of channels, membrane potential. Now we're going to talk about the membrane potential. So starting from our group from the very top, we pointed out the end result is that it's negative on the inside of the cell and it's positive on the outside of the cell. This is from your quiz. You remember the questions of membrane potential, meaning that if I were to measure the inside of the cell versus the outside of the cell, we would know that the inside would be about negative 70 millivolts. And that's our resting membrane potential. So what factors are on the inside of the cell, or what factors are really about the entire neuron, lend to that negativity? So
Potassium.
group number one, give me one reason.
Potassium moving out.
Negative membrane potential. Number one. What was that again?
Potassium moving out.
Leaky potassium?
Moving out.
Okay. Leaky potassium channels. Again, which direction would potassium want to move?
Out.
Out.
Outside.
Okay. So if I have these positive ions trying to constantly leave the inside, and that's what it does. It moves down that leaky channel. What's that going to do for the inside? Is it going to make it more positive or negative?
Negative.
Negative. Okay. So that's reason number one. And most of you guys got that. I'm happy to see that. But I didn't see the second reason. Group number two. What's reason number two?
Large size and able to
Large
ions.
large anions, right? And what are those large anions?
Stay.
Phosphates, proteins. We have acids in there. Tons of stuff. Even the organelles are huge. And they have a tendency to be negative. Group all the way in the back. Number three. What's the third reason? We have a third and final reason as to why it's negative on the inside of the neuron. Sodium potassium pump. Okay. And what is it about the sodium potassium pump that causes it to be negative? Go ahead, Eli.
More sodium going out than there's potassium going in.
Okay, great. So 3 positive ions going out, 2 positive ions going in. And are those, in regards to the sodium potassium pump, are these these ions that are moving through or that are being actively pumped through the sodium-potassium pump, are they moving down their gradient or up their gradient?
Upgraded.
Up the gradient, right? Meaning they're going from a low potential to a high potential. You're pushing those ions. If I'm taking that same example that I was talking about earlier, if I'm pushing all you guys, if you guys are ions, I'm shoving you guys into a corner, that takes work. That takes energy. And that energy is in the form of ATP. So now that we've established the negative membrane potential, we know that these all lead to being negative 70 millivolts on the inside. And if we were to measure out, let me change my thing here. And I'm going to scroll down a little bit and draw negative 70 millivolts. These are millivolts. I'm at negative 70 here. We know this is rest, right? So these are probes. Our probes are sitting one in here, one on the out there, and we know that the inside is negative 70 millivolts. That's it at rest with all these three contributing factors. Now that we're going to look at that, we see that you should know by now when we look at the ions, the direction of the ions, we talked about the concentration gradient. Now we know the electrical gradient. So let's revisit those. Let's take a look at sodium. Sodium, we already established wants to go in. Now would that be going, we have a positive ion wanting to go into a negative intracellular fluid. What's the direction of the electrical gradient? Which direction would sodium want to move in? Just looking at the electrical charge. It want to move inside, right? And then potassium. What direction is potassium? If you have a positive ion, which direction would it want to move electrically? Back in. So it would want to remain inside. And then calcium, we'll establish that later. That's okay. So that leads us to our negative 70. So now we've touched on all of these points right here. We know why the neuron is at rest. We know the direction that ions want to move. And we're at negative 70 at rest. Now let's take a look at the changes that would take place in membrane potential. Why would there be changes in the first place? Well, we're trying to lead that neuron to start to fire. Because if it ultimately fires, it fires an action potential, it shoots out a neurotransmitter. So the changes that would take place, we have to take a look at what's taking place with the graded potential. And the mechanism, we'll skip a little bit to the graded potential in that it takes place in ligand-gated channels. Where are our ligand-gated channels? Again, taking place in our dendrites. Actually, I should have had you guys answer that. Where are our voltage-gated channels? Group in the front. Where would you see the highest concentration of voltage-gated channels? What part of the light loop axon is the most sensitive portion? Axon hillock. So here we would see the voltage-gated channels. And what's so special about the voltage-gated channels? Well, any changes in the membrane potential would trigger these channels to open up. And the ones that we talked about, we had two types of voltage-gated channels. And I'll answer this one for you. It's sodium and potassium. Voltage-gated sodium, voltage-gated potassium. They're gated. It just needs some change to take place, and that change is the membrane potential that would trigger it to open up. But right now, we're not at that yet. We have to step back and take a look at our graded potentials that are taking place. Again, where is that taking place? The dendrites. We're trying to get our ions to move down the direction to the axon where it's most sensitive. So if you're thinking about sodium going in through those ligand channels, think of those as like heat kind of coming in. It's probably not a very good analogy, but you got heat, and you're trying to direct those flames, that heat, over to the area, that axon hillock, the area that's most sensitive to the voltage changes. Or specifically those ions that are moving in that direction. So now that we've got the changes that take place, we have depolarization, repolarization, and hyperpolarization. And so now I've got, and again, you're going to have to picture a neuron back here, firing neurotransmitters. And this is why it's sometimes a little convoluted, because I'm jumping to what's happening before the neuron and back out afterwards. So I've got a neuron right here, and it's shooting out a neurotransmitter, glutamate, which is excitatory. And an excitatory neuron should do what to the dendrites? What should it allow in? What type of ion? Or what ion, rather? If it's excitatory. Well, let's take a step back. Hold on. Let's take a look at this right here. Any fluctuations that would result in a depolarization, and depolarization in this case would be towards 0 millivolts. We have polarity where we have -70, 0 where we pretty much have no polarity anymore, and then back up to +30. So depolarization would be which direction, up or down in this graph?
Up.
Up. So this is a depolarization. Repolarization, well, depolarization is up. Repolarization is in which direction?
Down.
Down. And then, explain to me, I give you guys a question already, right? Yeah. Group. Next group. What exactly is hyperpolarization?
The overshoot.
We're not at the action potential yet. We're just talking about hyperpolarization. It's in your notes. Look at hyperpolarization. One goes up, the other one goes down. Okay. Go ahead. No problem. Somebody say it. What is hyperpolarization? Underneath the threshold. I'm sorry, underneath the
Resting.
underneath the resting membrane potential. So you're kind of in the right area that you're talking about an undershoot, but we're not talking about the crazy waveforms that are taking place right now. All we're talking about right now are just what ions would cause changes in the membrane potential. And in this case, anything below would be a hyperpolarization. So by virtue, that is the definition of what that quiz question was. A hyperpolarization is a dip below the resting membrane potential. So now that we've defined the terms, what we want to do next is take a look at the changes, the ions that would result in those changes. So group in the back. What would cause a depolarization? What would cause it to become depolarized, meaning making it more positive on the inside of the cell? What ion would cause depolarization? Sodium, right? Did I hear sodium? So sodium going into the cell. And let's take a look back over here. If I have sodium going down its concentration gradient and going down its voltage gradient, meaning I have a positive ion going into the cell, it's going to make it more positive, right? Now, what would cause a repolarization? Group in the front. Repolarization. What would cause it to become more negative on the inside of the cell?
Potassium moving out.
Potassium moving out.
Moving out.
I'll call it potassium efflux, sodium influx. Influx going in, efflux going out. And then hyperpolarization. Next group. What is the ion that causes hyperpolarization?
Potassium.
Potassium. That's not fair because that's on the quiz and I gave you guys the answers on this. So hyperpolarization is potassium also moving out. You have a positive ion leaving an already negative cell, making it more negative. Okay. So now that you see that in place, these little fluctuations that you see taking place right here, and let's assume it's under threshold, these little fluctuations that are taking place, whether it's a depolarization or a hyperpolarization, is that a graded potential or an action potential? Graded potential. And the graded potential occurs where? On our neuron. Where does it take place? Does it take place in the dendrites, cell body, axon, or axon terminal?
Axon helix.
Cell body.
Cell body.
Cell body or the dendrites. Okay? So now we're looking at what's taking place in here. So if I'm starting to lose you a little bit, let's kind of start to wrap that portion up. So now I've got a neuron. I've got a neuron on here that's shooting out neurotransmitters. I've got some that are excitatory, and I've got some that are inhibitory. So looking at glutamate, which is an excitatory neurotransmitter that's found in the central nervous system. If it's excitatory, what is it going to do? Is it going to depolarize or hyperpolarize? Depolarize, right? So I would expect the curve to up. Why? Because I have sodium coming in. This causes sodium to come in. And sodium going in causes a depolarization. And opening up a channel of one of these ligand-gated, one of these neurotransmitter-gated channels over here causes some sodium to come in. Jumping up ahead a little bit, group in the back. This might be a little harder question. What happens if I open up, if I got more glutamate, that opens up another channel, another glutamate channel. And that glutamate channel also allows sodium to come in. And those two take place at the same time. I get an additive effect that's taking place of now more sodium coming in through two channels. What is that additive effect called? Summation. And what two types of summation do I have? Spatial and temporal. This example right here of sodium's coming in at the same time due to our glutamate coming in and activating these ligand-gated channels. Is this an example of spatial or is this an example of temporal summation?
What was the question again?
Okay. I have sodium coming in at the same time, but two different places. Spatial. Okay? If I get this neuron right here to shoot out glutamate, and it opens up that channel, and then this neuron fires again and shoots another glutamate and causes it to open. I've got sodium opening up at two different times at the same place. What is that? Is that spatial or is that temporal?
Temporal.
Temporal. So all that comes down to is the times at which these channels open up, whether they're together or whether they're happening sequentially, is allowing ions to come in. Now that you know sodium coming in would depolarize, let's take a look at something that's inhibitory, like GABA. Let's say this neurotransmitter releases GABA. It's an inhibitory neuron. It shoots out an inhibitory neurotransmitter. Knowing that it's an inhibitory neurotransmitter, what type of ion would it be? Well, if depolarizing excites a cell, hyperpolarizing should not make it so excitable, right? Why? Because I'm hyperpolarizing. I'm moving further away from that one target that we're getting to later on, our threshold. So hyperpolarizing, we know, is potassium. So an inhibitory neurotransmitter comes in and allows which ion to move in? Inhibitory. What would make it less likely to reach threshold in these areas? What would cause it to hyperpolarize on the inside? Potassium. So potassium coming in to the cell, or even a huge negative ion like chloride. Chloride coming in would make this more negative on the inside. And that would hyperpolarize it. If it hyperpolarizes the cell, it makes the cell less likely to fire. If I have an excitatory neurotransmitter binding in, it makes that cell more likely to fire. And that's all due to the ions moving in, whether it's sodium for excitatory, or potassium, or chloride for our inhibitory. You guys with me? All right. So now that we have that in place, we're seeing the changes that are taking place, and I'm going to take a look, I'm just going to erase some of these right now. Looking at the sodium that's entering the cell, and let's just take it from the perspective of an excitatory neurotransmitter coming in, allowing sodium to come in through through the dendrites. I've got waves of sodium coming in. And where are we trying to get that sodium towards again? The axon hillock. So if I were to measure the amount of sodium in that area, I know this area, I've got a bunch of sodium in that area. Is it going to be more likely to be positive or negative in that area? Positive. Okay, that was kind of an obvious question. So if I were to measure around there, I know that area might be probably towards 0 millivolts. So if I measure the concentration here, high concentration. And as I start to move lower and lower, that sodium is going to start diffusing from a high concentration to a low concentration. And it wants to move in that direction. And eventually, when you sum up all that amount of potassium, and we get these waves of potassium making its way down, we know sodium is depolarizing that area. So here we could see it's probably around 0 millivolts. Oh, by the time you get over here, it's probably about negative 30 millivolts. And then by the time all that sodium makes its way down over here, it might be about negative 60 millivolts. Okay. That's due to the concentrations of sodium making its way down there. It's most concentration over here, and it's moving its way down. So what other ways, if I've got sodium coming in through one channel, and by the time I'm reaching the axon hillock, my concentration is not at its high, not at that threshold that I want to get to, which we know is negative 55 millivolts. Negative 55 millivolts. What's the significance of negative 55 millivolts? That's our threshold. And what does the threshold mean in regards to our voltage-gated sodium channels? It's excited, but it opens it up, right? So as long as I get to negative 55 millivolts at the axon hillock, which you already told me has the highest concentration of voltage-gated sodium channels, that triggers this whole thing to fire. But I've just got to get enough sodium in here to eventually make its way down where it's negative 55 millivolts to finally activate our voltage-gated channels. So if it's not enough, what I could potentially do is summate. I can get more neurotransmitters in there. If I get another glutamate to open up, then I get more sodium coming in. So now I got more sodium coming in. If I were to take a look at the millivolts here, it would probably be about 30 millivolts. Down over here, 0 millivolts. Back over here, maybe negative 55 millivolts. I've got a wave. I'm fanning the flames. I'm trying to get that sodium down to that area. So once that sodium makes its way down to the axon hillock, and we've got enough sodium, and it causes it to be more positive, up to the point about negative 55 millivolts, that opens up our voltage-gated sodium channels. And what happens with our voltage-gated sodium channels? Which direction does sodium move in? The direction that sodium moves in. Sodium moves in this direction. It moves on the inside. So now that you're at negative 55 millivolts, you've now got this, you've opened up our voltage-gated sodium channels. And now you've got a bunch of sodium rushing in. I'm going to draw this thing again. Now we're going to focus what's happening at the axon hillock, which has the highest concentration of voltage-gated channels. We're at negative 55 millivolts. We've depolarized enough that we get to negative 55 millivolts. And what was the other number that I had you guys memorize? Positive 30 millivolts. So we look at what's taking place right at here. We're starting to depolarize. We got sodium coming into the cell and making its way into the axon hillock. And once we reach negative 55, because there's enough sodium that came in through the dendrites, through the cell body, we've got enough sodium in there that it opens the gates open. Now we get this rush of sodium coming in. That's going to open up our voltage-gated channel. So we get to that point, and then the first portion that we're going to see, the first phase, we call the rising phase. Why is it rising? Why is it getting more positive on the inside of the cell?
Because the voltage gauge centers are open.
Let's, where did I leave off? Was it you guys? You guys answered one? You guys are next. Okay, great. So what's causing it to, what's causing it at this point, at negative 55 millivolts, why is it becoming more positive on the inside? Sodium entering through voltage gated channels. Okay, so that's a rising phase. Sodium rushing in. So we've activated, and technically what's happening at negative 55 millivolts is we're opening up our voltage gated channels, both sodium and potassium. So this one's a harder question. Why do we only see the effect of sodium in the very beginning? Yes. Which means sodium opens up faster. So if I got one gate, and if you were to picture this right now, we have two doors right here. This one's a voltage-gated sodium channel. That other one, the voltage-gated potassium channel. This one opens up really fast. You got sodium rushing in, right? That one is slowly creeping open. So the first phase we're going to see is a fast depolarization. We get a bunch of positive ions rushing into the classroom, making it more positive on the inside. Then we get to the point where at about 30 millivolts, and our sodium channel does what? Group in the back. Right at the very top, at positive 30 millivolts. What happens to our voltage-gated sodium channels at that point? They open or they close? They close. So it closes at that point. And then, now we're going to see the falling phase. What's causing the falling phase? Group number one.
Moving out.
Potassium moving in what direction?
Moving out.
Moving out. Which channel? What type of channel? Our voltage-gated potassium channel.
Yes.
Now that our sodium channel is closed out, we've got our voltage gate finally starting to open up a little bit more, and now you've got a bunch of positive ions rushing out, which does what to the cell? If I've got positive ions moving out of the cell, what's that going to do for the... It's going to repolarize? Did you say repolarize? Repolarize. Great. And that is what characterizes the falling phase. It's becoming more negative back on the inside, hence repolarizing, bringing us back towards negative 70. And then, because our, again, your name, last is second group back there? Diana, okay, great. As Diana was saying, potassium channels open up slower. So because our potassium channel is still open, we're bringing it back down from positive 30, negative 55, negative 70. It's going to stay open, and it's going to contribute to what's called the undershoot. And don't lose sight of where we're at. All this is taking place in the axon hillock, right at that point. This is that single point right there. I'm measuring the changes in the membrane potential. So now that we have the undershoot, we know that's due to the potassium leaving. And we're eventually going to make our way back to negative 70, back to rest. We didn't talk about a third type of pump. And that pump, I'm sorry, that pump is a sodium-potassium pump. It's moving the entire time to restore that membrane potential, because it's pumping out 3 positive ions back out, 2 potassium ions back in, and that's requiring ATP. So it's working the entire time just to restore it back. So now that we have that in place, we have the action potential. We explained the movement at all phases. At this point, if you were to plot the permeability, we were to take a look at the permeability of potassium. We'll see that potassium has a tendency to be open in the very beginning, and then it drops at that point. If you were to measure, this is sodium permeability. If you were to measure the potassium permeability, you would see it looks like this. And in your own definition, what does permeability mean?
Allow of ionization out.
The ability for a cell have ions move in and out. So the higher the permeability means more ions moving through. The lower the permeability, less likely ions to move. So looking at the permeability, we know that this area right here, where at its peak, this is when the sodium is rushing in the most. And that is what contributes to the rising phase. And then the falling phase is when sodium permeability drops, but permeability for potassium is rising, meaning potassium is leaving the cell. It's going to continually leaving the cell until we reach the undershoot, until the permeability stops. We're going to get to the point that our voltage-gated channels close, and we're back to resting membrane potential. But that entire time, I'm talking about what happens at that spot. I've just described that the axon hillock is now lit up. It went to threshold. And now if I can just zoom in, I've got sodium in that area. I've got sodium coming in. The concentration of sodium is now, and let's take a look at what it would look like a second from now. I've got sodium coming in through those voltage-gated channels. It's going to create a wave of sodium going into this area. It's going to flow in, it's going to flow out. But the highest concentration is right at that spot. If it were negative 55 millivolts in this area due to sodium coming in, negative 55 here, and you look at the wave of sodium, you notice that this area might be negative 60. Let's say now you're getting more sodium coming in through those voltage-gated channels, and now it's about positive, let's say 0 millivolts in this area, and right in those adjacent areas, it's about negative 55 over here. Remember, concentration is highest over here. You've got sodium wanting to move in both directions. That means when in this area, if it's close to negative 55 millivolts, it would want to trigger an action potential in that area. Group in the back. Why would it fire an action potential at this point?
Is this threshold?
It's at threshold, right? If all I need is negative 55 millivolts, that means anywhere surrounding in that general vicinity should mean we're going to reach threshold. So why doesn't it light up in that area back over here? Thank you for answering that. So refractory period. This place already fired. So if it already fired in that area, it's in a refractory period, meaning it can't fire again. Absolute refractory period. Next group. What does absolute refractory period mean? Refractory period is a period in which you cannot fire or you're less likely to fire. Which one is absolute? Cannot fire. To expand on that question, why can't that spot fire?
It has to get back to rest.
Has to get back to resting membrane potential. It's an okay answer.
There's no stimulation in the stimuli.
Go back to the guys.
Channels are inactivated.
What happened in this area right at that point? About a second ago. It just fired. So if it's already firing, it's not going to fire again. It's already in the middle of an action potential. So that's an absolute refractory period. Now, where would, and going back to here, and let's just draw black. Sure. This area represents absolute refractory period. Because we're already seeing the changes taking place at that point. The relative refractory period group in the back. Relative refractory period. If absolute refractory period means a neuron can't fire, relative refractory period means what? It can't fire. Absolute is cannot fire. Relative refractory period means, can it fire? Yes. But what do you need in order to elicit a response? Stronger stimulus. Why? Because we're pretty much in the undershoot. We're already hyperpolarized as is. And to get us back to threshold, we've got a longer way to go to get up to negative 55 millivolts. going back, in this period right here, go back to my original question. Sodium enters into the cell, and it moves in all directions. By the time it reaches over here, it's about negative 55 millivolts. I get an action potential, right? Why don't I get an action potential back over here? It's already fired, so it's in refractory period. So therefore, the action potential is most likely going, it's not most likely, it's going to only move in one direction. And it's not going to light up in areas that already fired. So negative 55 millivolts over here. Now I get an action potential half a second later, right at this point. Action potential. And at that point in time, it becomes positive on the inside. Going back to our graph. Once we reach that point, it's now positive on the inside for just a fraction of that second. And then we're going to go into the falling phase, into an undershoot. And as sodium's rushing into that area, again, that's going to cause another depolarization in this area, and another depolarization, another one, all the way until we reach the axon terminal. In the axon terminal, sorry for the group in the front, what was that last voltage-gated channel that's going to be present in the axon terminal? Calcium. So here we get our calcium channels. And calcium's going to come in. It's going to have our neurotransmitters. We've got a bunch of neurotransmitters that are literally just sitting in there, waiting to be released. They're going to come up and they're going to start to dock with the membrane. And there's these docking proteins that are present. And all calcium needs to do is come in and bind to those docking proteins, and that causes exocytosis of that neurotransmitter. And what's the whole purpose of that neurotransmitter? Muscle, nerve, or gland, right? It's going to come back and start this whole cycle over again. So if it's another neuron, it's going to come in. If it's an excitatory neurotransmitter like glutamate, it will depolarize that next effector target. If it's inhibitory, meaning it's a GABA, it's going to come in and make it hyperpolarized, making it less likely to fire. So looking at these, what's happening with our neurotransmitters is if we get glutamate and it's excitatory, it's going to depolarize the cell and make it more likely to fire because it's closer to threshold. If I have a negative or an inhibitory neurotransmitter, it's going to hyperpolarize the cell, making it less likely to fire. And the summation of all those neurotransmitters that are opening up those channels, allowing either sodium to come in, which would result in an EPSP, an excitatory postsynaptic potential. Means it's going to excite the next neuron. An inhibitory postsynaptic potential means it's going to make it less likely to fire. And now what you have to understand at this point, now that we've painted that whole picture, there's a lot of neurons that can come in and secrete excitatory, and a lot that'll come in and cause it to for inhibitory. And you'll be able to see this. Yes?
Why would we want inhibitory that doesn't transmit a signal?
Maybe I don't want it to fire.
Why?
Let's think about Parkinson's. You get a lot of tremors that are taking place. What's causing those tremors? What's causing those muscles to contract? Is it an excitatory neurotransmitter or an inhibitory neurotransmitter? Excitatory. The problem isn't excessive excitatory neurotransmitters. It's the lack of inhibitory neurotransmitters. These are unwanted movements. So I need to somehow suppress those. And that's autonomic. It's going to suppress and turn off something. Another reason, I have my heart rate. Think about that example that we saw with that car. Almost hit somebody, right? That person's looking at all that sensory stimulus that's coming in. I've got a car coming in my direction. It's going to start to excite the neurons in the brain. And those neurons that are responsible for the heart are going to start to excite the heart. So now I've got all these excitatory neurotransmitters that are releasing to increase the contraction of the heart. heart muscle. Now afterwards, after I start to cool down, my heart rate's going to start to slow down. What's going to govern it to slow down?
Inhibitory.
Inhibitory neurotransmitters.
So basically to keep the homeostasis level.
Yeah. If I want to speed it up and make it more excitable, use glutamate. If I want to make it less sensitive, I'm going to inhibit. And you're going to see that these two work hand in hand to modulate what's happening on that neuron, whether I want to make it more excitatory or make it more inhibitory.
So the whole purpose of the action potential is to use sodium and calcium and potassium to trigger and transmit those neurotransmitters outside?
Yes, for that neuron to trigger an action potential through
To
that
just
entire
throw
movement.
them.
When we look at graded potentials, which sum up to result in an action potential in the axon hillock, to cause an action potential to propagate, to release neurotransmitter, to target the next effector cell. It's just to send a signal across. You guys feeling a little bit better? All right. Okay, so with that, let's give you guys like a 5-minute break while I get situated, and I'm going to lead into our lecture. So I know today's lecture,